Hello everybody. So there's one more detail about the modified Bernoulli equation that we will discuss now. And this is going to be the last modification to Bernoulli equation that we will do. But before we go through the details of this equation, we need to quickly go through one piece of information that we will discuss later in details. I'm just going to discuss here the main idea of this detail, and then in chapter 8, inshallah, we will go through this in details. This is about the types of flow. So for any fluid flow in specifically in pipes and tubes, the fluid will flow in one of two regimes. One of them is the laminar flow, and the name is telling a lot about how this flow is or the nature of this flow. So for the laminar flow, the flow is flowing, or the fluid is flowing very smoothly, as if it's parallel layers sliding over each other. And this is usually the case for low velocities. While the other case is what we call a turbulent flow, and I think turbulence also tells a lot about how the fluid is flowing. So for a turbulent flow, the fluid is not flowing in parallel layers as it is the case in turbulent flow. It's flowing in a very chaotic way, and the flow creates a lot of eddies while the fluid is flowing. And this is usually the case for flow at high velocities. So this is what we need to know about these two types of flows for now. And we will, as I said, we'll discuss this later in chapter 8 when we go through this details of the viscous fluid flow. So what we want to discuss here is what we call the kinetic energy correction factor. And this is a correction factor that we use for getting accurate results of or accurate calculations of the kinetic energy. And to understand why we need this specifically for kinetic energy, not any other parameter in the energy equation, we need to recall this velocity profile. We discussed it before in the beginning of this chapter, and this is the velocity is 0 at the sides and it's maximum in the center, and this is how it looks like. So the average velocity we calculated it before using this, or it was calculated before, or the way we expressed it before was in terms of area. Now we are putting it in terms of radius. We can put it as 1 over r multiplied by the integral from 0 to r of u r dr. This is the same thing we did before. It's the formula that we use for getting any average value. So this is the average velocity, can be calculated using this formula. So when we calculate the kinetic energy as half mu square u average square, then we have an average value of the kinetic energy. Keep in mind that what we get here, when we calculate the average velocity, we don't actually calculate it using the integration. We calculate, or we measure the velocity, and the average velocity is what we get. When we have a fluid flowing in a pipe and we measure the velocity, this is actually the average velocity of the fluid. Not the total velocity. So there is some difference, of course, between the velocity at a specific point and the average velocity. It doesn't represent a specific point, it represents the average. So it's okay when it comes to just calculating the mass flow rate, it's fine. But when it comes to u square, then the differences will be big when you compare half mu square to the actual value of the kinetic energy, which is half u square dm, and the integration of half u square dm. This should be the actual kinetic energy, how we should calculate it the right way. And the dm is, we know that dm is rho u a, so u r dA, rho u dA, rho u dA. So it's rho u dA. And then you have we have velocity here and velocity here, so it's half u square u power 3. So you have half rho u power 3. So we have u power 3 here, and then we'll do the integration. So the difference between what we get here and here is big because of the high power of the velocity. It will maximize the difference, or will make the difference bigger between the actual and the average value. So this is why what we have here is in the average is not going to be very accurate. That's why we need to use a correction factor to account for the error. So again, before this point, we have one of two options: either to go with the accurate way, which is using the actual kinetic energy, and of course we know that the integrations are not practical to use in real life, or to modify the equation to account for this discrepancy between the actual and the average value. So what we do is we use what we call a correction factor, a kinetic energy correction factor. So the kinetic energy correction factor is defined as the ratio between the actual kinetic energy and the average kinetic energy. It's the ratio between these two. And based on this, if we want to get, we can easily calculate the average kinetic energy from this equation. So if you want to get the actual kinetic energy, which is the true value, we will multiply alpha by the average kinetic energy, and we can rewrite the kinetic energy, or the modified Bernoulli equation as we see here. It is so we define the equation as or it's going to be the same equation, but we just put an alpha here and an alpha here. So this is the correction factor. Otherwise, the equation is the same. And by using this correction factor, we have the kinetic energy term expressed in an accurate way, and will give accurate results. The value of alpha depends on the type of flow, and this is why we discussed the laminar and turbulent flow before. For the laminar flow, the correction factor is around 2, and this is because the profile in the laminar flow is very parabolic. It looks like this. For turbulent flow, it is close to 1. It's 1.04 to 1.1, and this is because for the turbulent flow it's not as parabolic as this. It's more like flat with a profile gradient, or the velocity gradient on the sides is high gradient, and then it's almost constant velocity throughout 90% of the whole area. We will discuss it later again, but what I mean that the average velocity is close to the velocity, the measured velocity in case of turbulent flow. That's why the correction factor is close to 1. So this is all. So now let's try to solve a couple of problems, just to practice more on the modified equation and see how we can integrate it with, or apply it on cases that were not possible to apply before doing the modifications of the equation. So the first is about a hydroelectric power plant. Hydroelectric power plant is a plant that produces electricity from hydroelectric power, which is the power of flowing water. The volumetric flow rate of water is 100 meter cubes per second, and the elevation is 120 meters to a turbine. So we have here this 120 meters through a turbine, and it generates power. The total irreversible head loss in the piping system from point 1 to 2, it's already, the 2 points are already highlighted in the figure, is 35 meters. So the losses, the HL is 35 meters, and the overall efficiency of the turbine generator, the efficiency of this generator with the turbine, I mean the overall efficiency is 80%. And we want to calculate or estimate the power output, how much electricity we're getting out of this. So what we do is what we used to do before, the same thing. We need to specify 2 points where we know some information, and we can apply Bernoulli equation between the two of them, or the modified Bernoulli equation between these 2 points. So I think it's clear. I mean, there is no other option we have than these 2 points, 1 and 2. We know that both are open to the atmosphere. Both are large areas, so the velocity of the two surfaces is 0. The difference in elevation is 120 meters, and we can now apply the Bernoulli equation, or the modified Bernoulli equation between these 2 points. So based on what we said, the two pressures will cancel out, the velocities will be 0, Z2 is 0, we take it as the reference, and Z1 is 120 meters. We don't have any pump, So the H pump is going to be 0 as well. So we only have three terms left: Z1, H turbine, and H losses. We know that Z1 is 120 meters, H loss is 35 meters, so the equation will end up with the turbine head is 85. Remember, this is an important thing, that what we get here is the extracted power, or the extracted head, H turbine E, which is the extracted, how much head the fluid lost, power, I mean energy head, of course, that the fluid lost. This is not how much electricity the generator will produce. Okay, so from this we can calculate the work of the turbine, the extracted work of the turbine, by just multiplying this by mg, m dot g, of course. We don't have the mass flow rate, but we know the volumetric flow rate and we know the density. So this density times the volumetric flow rate is the mass flow rate times g times the H turbine, which we calculated. So this is the power that the turbine will produce, how much watts or joules per second. This is not the energy that the turbine will produce. This is how much energy the water will lose. To know how much energy will be produced as electricity, we will use the efficiency. We know that the generator efficiency, overall efficiency, is 80%. So 80% of this energy is going to be converted to electricity, which will be 66.7 million watt, or 6.7 megawatts of power. So this is it. So if you compare this to what we did before, we just have three more terms, and we just need to account for the parts of the or the terms that have values here, like the turbine and the losses. This is the only difference from what we did before. Now let's check the other problem. We have here a similar case, but it is a pump instead of a turbine. So we have what we call a submersible pump. It's a pump that works while it's immersed under the surface of water. It has electric power of 5 kilowatt. This is how much energy, electric energy, is consumed by the pump, and its efficiency is 72%. And as we see, it pumps the water to a pool at 25 meters high above the surface of the lake. And the head losses is 4 meters, and we need to know the rate of water discharge. So again, we need to pick 2 points to apply the modified Bernoulli equation to. So this is point 1 and 2. These are the 2 points that we have. The same thing, the two pressures are atmospheric pressure, the two velocities are 0. The difference in elevation is 25 meters. There is no turbine, it's only a pump. And that's why what we will have here is that H pump is Z2 plus HL. Z2 is 25 meters and HL is 4 meters, it's given here. So the pump head is 29 meters of head. And now if we want to calculate, I don't remember what was the requirement. The discharge rate of water. So we want to get the discharge rate of water. So we know now how much head, the usable pump head. This is the usable pump head. Remember, all the terms that we include in this equation are related to the fluid itself. So this has nothing to do with the electric power. So we know the efficiency, and this is the ratio of the energy that the pump is consuming to the energy that the pump is producing. So if you do the math, we're just using the equation. This is the efficiency times the electric power is the work of the pump, and if we divide this by GH pump, we get the mass flow rate. Or we can write the equation as the work pump usable is mgh of the pump usable. The usable work of the pump is the efficiency times the electric power of the pump. We know all this information. This is 5 kilowatts, which is 5,000 watts. The efficiency is 72%, and the H pump is 29 meters, which we calculated here. From this, we can get the mass flow rate of the pump, of the water through the pump. So this is all for this chapter. And inshallah, next video we're going to start with one new chapter, which is chapter 6, I think. Yeah, chapter 6. So I'll see you then, inshallah.